Okay, so now that we've talked about one-to-one functions, we can talk about inverse functions. So being one-to-one is important in order for us to be an inverse because we've got to make sure that we have this unique x and y relationship. So if you kind of think of this as a like a plane ticket, and you wanted to go from, let's say, Orlando to Miami, if you were to buy a round-trip ticket, you go from Orlando to Miami, you want to go back to Orlando again, right? You don't want to go from Orlando to Miami and then back here at Baltimore, okay? So this is what we're looking for. We've got to have this unique relationship and know that the x and the y values, there's only one relationship that works for each one. All right, so when we looked at functions before, this was the relationship. We were going from x to y. So these are our x's, these are our y's, or domain and range in the general sense. Okay, so we're going from our domain to our range, and this is what our function f does. So now we're going to introduce the inverse function, and the inverse of f is written like this. F to the negative 1 is the inverse of f, or f inverse. Okay, normally a negative 1 in math means a reciprocal. That's not what it means here. It means the inverse of the function f. This is function notation. Okay, so if f goes from 1 to a, if f goes from x to y, we need the inverse to take us back again. Okay, so that's what f inverse needs to do. So our function goes from x to y. Our inverse is going to take that y value back to x. So our inverse needs to undo whatever our function does. And that's the definition. So in math terms, we say that f of f inverse will take us back to x, and f inverse of f will also take us back to x. So what that means is, let me get a different color here. If we're starting at 1, okay, the function is going to take us to another value, and then the inverse is going to take us back again. Okay, or in other words, let's get a different color. Okay, if we're starting here, then the inverse is going to take us to a value, and the function is going to take us back again. Okay, so basically the function and its inverse, they undo each other. All right. So we've already seen a couple of functions like this. So we know that if you have x squared and you take the square root, that those will cancel out as long as x is positive. And if we have cube and cube root, they will cancel out. We also saw them graphically, which we'll look at in just a minute. So first, let's look at these in terms of function notation, and let's verify that we have two inverses. So let's verify that f of x equals 3 minus 2x and g of x are inverses. So g of x equals negative 1/2 x minus 3 are inverses. Okay, so I want to verify that these two things are inverses. So how do we do that? We use this definition right here. Okay, we use the composition of functions that we just talked about in the last section. So if we do f of g and g of f, they should cancel out and just leave us with x. So let's do f of g of x, and then we'll do g of f of x. Okay, so remember what we do here. We're going to take g of x, which is this thing right here, and we're going to put this into f. Okay, so we're going to take this, and we're going to put this into f. So anywhere that there was an x is now going to become this, negative 1/2 x minus 3. And it might look a little bit cumbersome at first, but you'll see how this works. Okay, so this right here is going to be replaced by negative 1/2 x minus 3. Okay, so now it's going to be a matter of cleaning this up a good bit. Okay, so we've got 3, and then when we distribute this, this is 2 times 1/2 times x minus 3. So it's actually like this. Okay, so we're not going to distribute that 2 over everything. We're actually just multiplying these two together. So the 2 and the 1/2 cancel. That 2 times 1/2 just gives us 1, and negative negative gives us positive 1. So we actually have 3 plus 1 times x minus 3, and we know that 1 doesn't do anything. So we've got 3 plus x minus 3, and now we see the 3's cancel, and we're left with just x, which is exactly what we want. We want everything to cancel out and just have x left over. Okay, now, usually if one direction works, the other direction will work as well, but let's go ahead and check it. We did f of g, so now let's do g of f. I'm going to jump up to here. So now we're going to take f and put it into g. So f is this right here, 3 minus 2x. 3 minus 2x, and we're going to put that into g. So where there was an x is now going to become 3 minus 2x. So we're going to have 3 minus 2x minus 3. Okay? So we took this right here and we put it into g. Okay, that's what we replaced. So x became 3 minus 2x. Alright, so let's clean this up a little bit. We could distribute the 1/2, but let's simplify inside the parentheses first. So we've got negative 1/2. These parentheses aren't doing anything here because we've got 3 minus 2x minus 3. So that's 3 minus 2x minus 3. And we've got, that's a minus. We've got 3 minus 3. Again, those are going to cancel out. And we've got negative 1/2 times minus 2x. So again, 1/2 times 2 is 1, ends up positive, and we're left with just x. Okay, so that's exactly what we're looking for two functions to be inverses. They have to come down to just x and nothing else. Okay, now let's take a look at what happens with inverses graphically. Now we've actually looked at inverses graphically, we just didn't really talk about the fact that they were inverses. But if you go back to section 3.4 when we were doing the library of functions, we looked at x squared and square root of x, and we looked at x cubed and cube root of x. And if you remember, we saw that these graphs were related, and we saw that the tables were related. And if you remember looking at the table for one and then looking at the table for the other, what happened in those tables is that the x and y values were switched. Okay, x and y values were switched. So let's think about what the function does. Remember, the function takes us from x to y, and the inverse takes us back again. Okay, so x becomes y, y becomes x. So when you look at inverses, that's exactly what happens. The x and y values switch. So let's just remember what these look like. Okay, for x squared, we're only going to be able to look at one side of the graph. So half of a parabola, remember we kept saying half of a parabola on its side, this is y. So half of a parabola and the square root. Okay, and then let's look at x cubed and cube root. And remember, x cubed looks like this, and the cube root looks like this. Okay, so this one's the cube root, and this one is the cube. And this one is this half of x squared, and then this is the square root. Okay, so we saw in the tables that the x and y values were switched, and we see here that these graphs are very similar, and we kind of noted that in what they were doing, but what they actually have is they have symmetry. When you switch the x and y values like this, what happens is you end up with symmetry. Ooh, hold on, I got off track a little bit there. You end up with symmetry across the diagonal x equals y. Okay, and same thing here. There's symmetry across the diagonal x equals y. Okay, so graphically, inverses have this type of symmetry, and to find an inverse, you just switch the x and y values. Okay, so the graphs are also going to be very much related for inverses. Okay, so now we know how to identify inverses. We know what they look like, and we know that we can verify them, but how do we actually find an inverse? If we have a function, how do we know what function would undo it? And would that function always work? Well, there is a way to find inverses. Let's say that we want to find the inverse for f of x is equal to 1 minus 3x. Okay, so how do we find an inverse? Well, we use the same idea as those tables, that the x and y values have to switch. Okay, so the same thing from the tables and the graphs that we just talked about, we're going to use the same idea here. So the first step is that we've got to get out of function notations that we're looking at x's and y's. So let's switch this out of function notation. Okay, so we're going to switch to x and y for our first step. This is first step. Okay, so now we're in terms of x's and y's, and then the second is going to be to use this concept of the x's become y's and the y's become x's. I would highly recommend that you make some sort of line here showing that you are switching to the inverse. Okay, because this is not something that we normally do in math. We are literally going to change the x's to y's and the y's to x's. Okay, so I recommend doing some sort of marking here so that you remember that that's what you did in this step. All right, so the y is going to become x, and x is going to become y. Okay, nothing else in the equation changes. Literally, the letters change place. And when you do that, you will have the inverse function. Okay, so our second step is to switch the x's and y's. Okay, so all of the x's become y's and all of the y's become x's. So we're literally going to swap them. Let's say swap here so we don't, because we've got the same wording in both of these. Okay, so swap the x's and y's. Okay, so what you have here is the inverse function, but we really want to get it back into function notation, which means we need to solve for the new y. So solve for the new y, and we're going to have we're going to want to get this y by itself, so we're going to subtract 1. We're going to have x minus 1 is equal to negative 3y, and then we need to divide the whole thing by negative 3. Okay, so we've got x minus 1 is equal to negative 3, and that's equal to our new y, and our new y is the inverse function. So you can write equals y, or you can write equals f inverse of x. So these are the 3 steps to finding our inverse function.